All right, class, we're going to continue with solubility product today. This is part 4. Now, remember, like we said, for example, lead 2 iodide is a solid, is not soluble based on the solubility rule, but we know everything, even insoluble solid, have some solubility. So there's an equilibrium going on for insoluble solid because some of them will dissolve in water. And this is the equilibrium. We've been doing this over and over again. And to some degree, some of the lead 2 iodide will dissolve into ions. And because this is an equilibrium and we have a double arrow, we have an equilibrium constant, we said. And the equilibrium constant is called Ksp. Now, equilibrium constant is for equilibrium, is when we are at equilibrium, right? Basically, what is the max that can dissolve? What is the max lead 2 iodide that can dissolve and make a saturated solution? Again, what does a saturated solution mean? Means the max that can possibly dissolve has dissolved. If you add any more, the precipitate will happen. You cannot add any more. Okay. Now, we want to know if a reaction is at saturation, if a reaction is at equilibrium, or we can keep adding the solid. So I want to repeat this one more time to make sure we're on the same page. So Ksp means you are at equilibrium, right? The max that can dissolve, it has dissolved. You have a saturated solution. You have dissolved the max amount you can do. For example, for lead 2 iodide, if I add any more, I'm just going to have precipitate in the solution because I cannot dissolve any more. Now, we want to know if the reaction is at equilibrium. To know if a reaction is at equilibrium or no, again, this is the same as when we were just talking about any simple equilibrium. We have to figure out the Qsp. We have to figure out the Qsp, compare it to Ksp to figure out where we are, in a reaction. So nothing really has changed. Now again, Qsp is based on the given sets of concentration. Qsp is the same form as Ksp, but the concentration are not necessarily the equilibrium values. The concentration are during the reaction. Okay. Now what we are going to do, and if you know that, you have to compare Ksp to you have to compare Qsp to Ksp to figure out where we are. Are we at equilibrium? We're not at equilibrium. What's going on? Again, Qsp is the same formula as Ksp, but the concentration are not necessarily at equilibrium. The concentration we have right now during the reaction. So we're going to compare Qsp to Ksp. Now here are the options we have. Option 1, Qsp equals Ksp. If Qsp equals Ksp, what does that mean? That means we are at equilibrium. We are at equilibrium. Neither the forward or the reverse reaction is favored. We are at equilibrium. Okay. Now, another option would be, you can probably guess what I'm going to say, is that Qsp, what just happened? Qsp would be less than Ksp. Now, what does that mean? So, we have not reached equilibrium. There is no PPT and there is no precipitate. We have not reached equilibrium, right? We have not reached equilibrium. Okay? And if I had to draw it, this is what I would draw. Now, what happened if Qsp is less than, we just did less than, is more than Ksp? If a value is higher than Ksp, What does that mean? That means we are beyond saturation. We are beyond saturation. We are beyond saturation. There is PPT. There is PPT. You cannot dissolve any more solid. And if I had to draw an equilibrium arrow, this is what I would draw. Now, don't forget that. So these are the possibility. But as you comparing Q to KSP, don't forget that QSP and KSP is product over reactant, right? It's product over reactant. So you don't really have to memorize this. Just remember it's product over reactant. So if QSP is more than KSP, what does that mean? You have too much of the product, right? You have to shift to the other side. Okay. Now, let's do the next part. So now that you understand this, let's go to the next. Let's do a practice problem. Now, here is a keyword to look for. Will a precipitate a PPT form? Every time they ask you, will a precipitate form, almost every time, what do you have to do? You have to involve QSP because you have to figure out what's going on right now and then compare it to KSP. Okay, so here is our next problem. So here's our problem. Now, again, every time they ask you, will a precipitate form? Every time this is a question, you're really asking for QSP because they're telling you these are the concentration right now. Are we at equilibrium? You're not at equilibrium. We can add more, or no, we are beyond saturation. Okay. Now, in this problem, is very interesting. There are two ways to do this. You can actually be smart about it, and you can do less work. But I'm going to do more work, and I'll show you how I could have done less work. So they take in silver nitrate, and they add in it to sodium chloride. This is a double replacement reaction from Chem 1A, right? If you remember, in is with inis, out is with outies. If I do that, what I end up getting is silver chloride plus sodium nitrate. And all these solutions, all these reactions are happening in water. If I add two solid together, nothing happened. I just have a mess. All these reactions, water is a medium to make the reaction go. So we would have to look at the solubility rules and see what happened to each one in water. If you look at the solubility rules, silver nitrate is soluble. It would break up into ions. Sodium chloride is soluble, break up into ions. These are double replacement reaction from Chem 1A. Review them if you must. Silver chloride, based on the solubility rule, it would not break up. And sodium nitrate will break up. Basically, all the 1A group, they always break up. All the nitrate, they always break up. Okay, what are my spectator ion? My spectator ions are sodium and then nitrate. So what I end up with is silver plus Cl forms silver chloride, and that is my precipitate. That's my precipitate. This is a precipitating reaction because this is my PPT. Now, you didn't have to do any of this. Why not? You didn't have to do any of this if you were smart about it. And I know you're smart. Here's how you would do it. KSP is for silver chloride. KSP is for an insoluble solid, right? So this is a hint. Given the KSP, this should be a big hint that, the KSP is for silver chloride. That must be my insoluble solid because KSP is for insoluble solids. Okay? All right. So now I'm going to do this. I'm going to say, okay, that is great. So silver chloride is my insoluble solid. I didn't need to do any of this because the KSP was for silver chloride. So that must have been the insoluble solid. But again, you can always do that to convince yourself. So here is this, and KSP is equal concentration of silver times concentration of Cl. Okay. Now, we need to figure out QSP and then compare the QSP to KSP. Now, if you read this question, I'm going to go to the next page so I have more room. I need to figure out the concentration of Cl and the silver right now. I need to plug it in and then figure out QSP and then compare it to KSP, because QSP and KSP are the same formula, right? Okay, now my concentration of Cl is what? If you read the question, it would be 0.050 molar. How did I get that? Because what you're adding for NaCl, you are adding 50 ml of 0.05 NaCl. Is a 1-to-1 ratio, right? So what you have, I'm going to write this down just to make sure. So NaCl, which everything would break up into Na and Cl plus, and NaCl is 0.050 molar. So what I would have 0.050 molar sodium chloride, right? It's a 1-to-1 ratio. Okay, that is my Cl minus, because that's where my Cl minus come from. Now my silver concentration, where does that come from? My silver concentration, what I give you the grams. I tell you I have 1.00 grams of silver nitrate, right? Okay, I don't have concentration. I have to convert grams to moles using molecular weight. 1 mole is 169.9 gram. 169.9 gram is the molecular weight of silver nitrate. So the grams cancel out. So I have that. Again, this is 1 mole of silver nitrate. But silver nitrate is not what I want. What I want is silver. They have a 1-to-1 mole ratio. They have a 1-to-1 mole ratio, which makes it so much easier. So now the moles cancel out. What I end up with moles of silver nitrate. What is that number? That number is 5.9 times 10 to the minus third moles. Okay? Again, molarity is moles per liter. Now, how much of it do I have? This was added to a 50 ml solution, right? So 50 ml solution. So I have 0.050 liter. What I end up is 0.118 molar for silver. Okay? So this is my Cl, this is my silver. Again, silver nitrate is where I get my silver from. Sodium chloride is when I get my chloride from. I do a little stoichiometry and mole ratio, and I figure out how much of each one I have. So far, so good. Okay, this is how much I have. This is how much I have. So now I want to plug it back into QSP. I want to plug QSP again. It's the same as KSP. It would be concentration of silver times concentration of Cl. What is my silver? My silver concentration is 0.118. What is my Cl concentration? 0.058. In concentration is molarity. So I'm going to do that. What I end up getting is 5.9 times 10 to the minus third. That is my QSP. Now compare the QSP to KSP and then tell me what can you tell me about it. QSP is larger than the KSP which is given in this problem, right? So the QSP, here's my KSP. My QSP is a larger number than KSP. Now what does that mean? That means, are we at equilibrium? We're not at equilibrium. At equilibrium, the QSP would equal KSP. That means there is no precipitate. There is no precipitate when you have QSP equals KSP, right? You're at equilibrium. Now, what does it mean here? QSP is larger than KSP. What does that mean? That means you have precipitate, right? That means you have precipitate. You pass the saturation. You pass the saturation and you have precipitate. Okay, so every time they ask you, will a precipitate form? What's going on? You would look at the concentration of the reaction right now. What are the concentration of all the values? You plug it in, you figure out QSP, and then you compare QSP to KSP. If QSP equals to KSP, that means there's no precipitate. You're at equilibrium. If QSP is larger than KSP, that means you went over it. You have precipitate in the solution. All right, nice job so far. Now, we're going to do one more thing, which is very useful, and that is fractional precipitation. That's our next part. Fractional precipitation, which is again, it's kind of continuation of QSV. Now, fractional precipitation is basically a technique to separate the ions by adding a reactant that would precipitate it out. So I have a bunch of things in a solution. I want to separate it out. You can selectively precipitate ions out one at a time. Okay? So I want to repeat that again. So fractional precipitation, what is that? Let's say I have a bunch of ions in a solution. I can add a reactant and selectively only precipitate some of them out and not the rest of them. Sometimes we have that. Sometimes we have a solution, it has different ions, and we will just want to extract one single ion of that. And we could do that. Now, let's do a practice problem. Let's do a big practice problem. Okay? Here's our problem. Okay? So I'm actually going to draw this out because this is a really important part of this class for you guys to learn. Because this is one of the few things actually it could come back in organic chemistry too. Here's my round bottom flask. I know it looks like a pumpkin. My drawings are not the best. I have a solution. Okay? Now, in this solution, what I have, based on the question that I just gave you, this solution has sodium hydroxide, potassium carbonate, and sodium sulfate. Okay? These are all 100% soluble in water, right? All 1A group, it would dissolve in water and break up into ions. Potassium is also the same. K+. Carbonate, remember the solubility rules from Chem 1A. Sodium sulfate, the same thing. It would break up into sodium and sulfate. Okay? So again, these are all soluble salts. They would dissolve 100% in water. Okay? They would be in solution. They would be aqueous. So they would exist as this. This is what they would be existing. So what I have in here, what I have in this solution, I have floating around sodium plus, I have floating around OH minus, I have floating around potassium, I have floating around carbonate, and I have floating around sulfate. These are the stuff that I have floating around. You guys agree? Okay. Now, this is my solution again. This is my solution because it has these three. These three break up into this ion. I have sodium, I have hydroxide, I have potassium, carbonate, sulfate. You get a bunch of these floating around. Now, what am I going to do? What I'm going to do now, I'm going to add lead-2 nitrate. Again, remember, all the nitrates are also soluble, right? So lead-2 nitrate will break up into ions in water, Pb+2, and then nitrate. 2 nitrate to be exact. Okay, so when I add this, what am I adding? I'm adding nitrate and I'm adding Pb to this solution when I add lead-2 nitrate. Okay. Now, Pb could combine. The Pb could combine with potassium, with not potassium. The Pb could combine with what? It could combine with carbonate, with hydroxide, and with sulfate. Again, this is plus. It cannot combine with another plus, right? You can't have two cations together. To have an ionic compound, you have a plus, you have a minus. You have a cation, you have an anion. So who could Pb go and react with? Pb could go and hang out with carbonate, with hydroxide, or with sulfate, right? And it could also go and hang out with nitrate, but if it hangs out with nitrate, it will just break up again because lead-2 nitrate is soluble in water, right? So it could also go and hang out with nitrate, but if that happens, it would just break up with that. But it could go and hang out with these three ions. Really good so far. Okay, so now let's have a little chart. Okay, so now before I show you the chart, let's make sure you're on the same page as me. So what this problem said, what you have these solids in water solution here. And we know these are all soluble in water, so I have these ions floating around in the solution. I add lead 2 nitrate, which also breaks up into ion in water. Is water soluble? All the nitrate are always water soluble. They break up into water. 1A group, they break up into water. And don't forget those things. Okay. Now, lead 2 nitrate will go. We'll also have these two ions floating around. And again, lead, remember, plus and minus, they make a ionic compound. So lead cannot really combine with potassium or sodium, right? If it does, again, it doesn't do anything because you need a plus minus, not plus plus. They both are cations. It could react with carbonate, hydroxide, or sulfate. It could combine back with nitrate, but it would just break up again. If it combines with nitrate, it would just break up again. So lead to carbonate, hydroxide, and sulfate are our three possible solid that could be formed. Okay, so these are the three possible solid that could be formed, and then what I've been giving you, these are their KSP value. Okay, and in this question they told you how much. You have 0.01 molar concentration of these ions, the hydroxide, carbonate, and sulfate, because again those are 1-to-1 ratio. All right, and I have those concentrations. So what am I going to do? The question is which one is going to precipitate out first. So I have lead 2 sulfate, again goes back and forth to lead plus 2 and sulfate, that doesn't change. And I can do the KSP, right? You know that I can do the KSP. Okay, so let's do the KSP for this one. Again, the KSP is the concentration of lead plus 2 times the concentration of sulfate. Okay. Now, my KSP is what? My KSP is 1.8 times 10 to the minus 8. Now, for lead, I'm going to put X. Now, sulfate, I know is 0.015. Okay? If I solve for X, I get 1.2 times 10 to the minus 6. Okay? So now, what does this mean? What does this mean? That's the concentration of lead needed to precipitate the sulfate out. That's the concentration of Pb plus 2 needed to precipitate out lead 2 sulfate. Okay, so that is the concentration of lead I would need in order for the sulfate to precipitate out. So if I'm adding lead 2 nitrate to these things, this is how much lead I would have to add before the sulfate can precipitate out. Okay, so that's lead 2 concentration needed to precipitate the sulfate out. To precipitate, actually I'm just going to say to precipitate the sulfate out. So far so good? Okay, now we're going to do the same thing. For lead 2 carbonate. We're going to do the same thing for lead 2 carbonate. Okay, I'm going to do the same thing here. The same thing that I just did over here, I'm going to do the same exact thing over here. So again, the KSP is going to be the concentration of Pb times concentration of carbonate. What is my KSP? 1.5 times 10 to the minus 13. I want to figure out how much lead I need in order to precipitate out 0.05 molar carbonate. Okay, if I solve for X, I get 1.0 times 10 to the minus 11. Again, this is the concentration of lead I need to precipitate out the carbonate. Okay, to precipitate out the carbonate. You know what's coming next, right? The next one I'm going to do is lead hydroxide. Again, you guys know the drill. To do a equilibrium equation. So far so good. Now KSP, let me write the KSP so it's a little bit nicer. is a concentration of Pb times concentration of hydroxide to the power of 2 this time. Okay, don't forget. Now, the Ksp is 2.8 times 10 to the minus 16. This would be X. Now, the hydroxide is 0.05 to the power of 2. Again, the hydroxide, the carbonate, the sulfate concentration is given to. You already have these concentrations, so you don't need to do anything. So, what do I get for X? For X, what I end up getting is 1.2 times 10 to the minus 12. Now, the X, again, is my lead concentration to precipitate out hydroxide. Now, this is a really hard problem, I know, but also this is going to come back so many times, and if you understand this, we're in a really good shape. Again, fractional precipitation is when you selectively precipitate things out. This is what I have in the solution, right? These are the ones I have floating in the solution. I'm going to add lead 2 nitrate to this solution. I'm going to add it drop by drop, drop by drop. I'm going to add this, okay? If I drop by drop, I'm going to add this. So lead is not going to do anything again with the cations. Plus on plus doesn't do anything, doesn't matter. Now lead, sometimes it could recombine with the nitrate, but it would just break up again. But lead could also go on and react with hydroxide, carbonate, and sulfate. And if it does that, it would form these compounds. It would form these compounds. These are the Ksp for it. Now the question is, as I'm adding the lead, which one is going to get precipitated out first? The sulfate, the hydroxide, or the carbonate? Which one is going to precipitate out first? Okay, so I did that. So this is how much lead I need to precipitate sulfate. This is how much lead I need to precipitate carbonate. This is how much lead I need to precipitate hydroxide. Okay, so now you tell me, what is the order of precipitation? What is the order of precipitation? So here is going to be the order of precipitation. You do this before you look at my answer. It would be lead hydroxide, then it would be lead carbonate, and the last one would be lead sulfate. Now, why is that? Because I need the least amount, right? You have to look at these values. Again, as you make in the order, make the smaller guy to be the first or the last, right? Don't make it to be the middle. So here is my lead 2 sulfate. That's my largest number. That's my largest Pb. That's the most Pb I need to precipitate it out. Now, if you come over here, this is the smallest Pb I need to precipitate out. So I don't need much Pb. So as I'm adding the Pb, this reaches first, this is going to go, then it's going to reach this amount, it's going to go, then it's going to reach amount, then it's going to go and precipitate out. So this is the order of precipitation. Order of precipitation. So far, so good. Okay. Now, I want to do a side note before I end this lecture. Again, go back to this lecture again. I know it's a little bit crazy, but if you look at it a couple times, hopefully it will click. Here's a side note. You remember how we said X is molar solubility? How much of the precipitate will dissolve? Now, the higher the X value, remember, it means it's more soluble. It means it's more soluble, right? It means it's more soluble. Okay. That was just a little side note for you guys if I ask conceptual question. But in this problem, again, I figured out how much lead I need to precipitate each one out. This was the most amount of lead I need to precipitate out. That's going to be the last one to PPT. But this one is such a small amount of lead I need to precipitate this out. If I add a little lead, that will precipitate out. All right, nice job. We'll do more practice problems next time.